Yes, thank you everyone for joining our computational thinking and problem solving workshop today. I think I know almost everyone in the meetings room. Let me admit a few more people here. But in case we haven't met before, my name is Hui. I'm from the Hertie School Data Science Lab. I help to manage most of the day-to-day work and research of the lab, and also support with our Masters of Data Science for Public Policy, the MDS here at Hertie School. This workshop was actually requested by quite a few number of students in our MDS program to support with their technical learning. And this stems from the difficulties of, I guess, learning and solving coding problems, especially those that we might encounter in technical interviews. And so to preface, I have to say that solving coding problem is always a difficult problem. It's always a difficult challenge. No matter how long and no matter how much you do, and no matter how long you have worked in the industry, but if you try to adopt a mindset that is like a fun challenge, like a game to beat, much like a chess game, then it's actually gets much easier with time. And just like chess, it gets much more fun and exciting when you learn to use a strategy and have an arsenal of tools that you can use when solving these problems. And so the information that is presented here today is my personal understanding of computational thinking. It is still an evolving field, pretty much, and it's changing every day. Each person has a different approach to solving these types of problems. So feel free to maybe drop out, or perhaps if you have a better idea of how to proceed with these kind of strategies, you can please also raise up your hands and put in your opinion as well. And yeah, feel free to also drop out anytime if you think that the information is presented here is too simple for you and you are already very much well aware of everything. So we'll go through some first. Change the slides here. So first, we will go to some of the motivations of why we should learn more about computational thinking, and what does computational thinking actually means, the methodologies and the different common strategies that are often used by people in the industry to solve coding and programming problems. And we will also maybe have one or two examples to demonstrate how we can actually apply these strategies in different contexts. And first, sorry, let me admit a few more people in. First, in terms of motivations, why do we care about computational thinking and problem solving, and what can it actually bring to our life? And there's a couple of obvious reasons you probably already know. So first is it helps quite a bit with your coding journey. It helps, this basically goes without saying, whenever you work on a coding problem, whether it is to build maybe a machine learning model, or perhaps to build a mobile or web applications, it always helps to have a logical strategies on how you can solve the different problems that you might encounter when you create and work with these things. And secondly, it helps with technical coding interviews. It very much depends on the types of jobs that you're applying for. So a lot of times, maybe you're applying for purely technical roles. And so for these type of roles, these jobs interviews are very much surrounding coding and technical questions. And so, and this is especially true if you're applying for big tech companies or maybe applying to startup, for example, and you will most likely encounter these questions and these coding problems, and you will be able to apply these strategies into these interviews. And finally, it might also be of some help with perhaps your daily life or your work. And it is not a silver bullet that is the solutions to every problem, but it certainly can be a very viable and good approach to a lot of problems that you might encounter in your work or daily life. And these are the lessons and principles. It includes how to pick out the essential details of the problems and how to perhaps formulate a problem in a way that computers and human can understand more easily, and how to follow through a problem-solving process in a way that the process can be automated. And these should be important to anyone, and not just people working in IT or people working in data science And because it's basically the aim of the whole process is to distill information, to distill knowledge. And beyond the understanding of these problems is also to empower everyone to not only being able to solve a problem, but also perhaps come up with very elegant solutions to carry out the task more efficiently and quickly. And so first we'll come to maybe a definition of what computational thinking actually is. There is still quite a lot of debate, and people are still trying to come up with a very perhaps short, concise, and elegant definition of what it is. But these are basically some of the best possible explanations of what computational thinking is. And from the sound of it, it seems a lot like how to think like a computer, but that's not entirely true. Mainly because computers don't actually think, they just follow orders, as you probably know very well. But those orders that the computers follows are not normal, they are very specific. And so if you want a computer program to do something for you that is useful and serve a purpose, then these orders have to be very highly specific, and it has to be logical, it has to have interconnecting tasks, and a very tailored approach to these tasks that you want to solve. And so computational thinking is actually the ability to formulate your thoughts and framing your problems into these specific orders that the computers can process and execute. It's basically also a mental activities for abstracting problems and formulating solutions that can be automated. And it's a mental orientations to formulating problems as conversions of inputs into outputs, and looking for algorithms to perform these conversions. And these inputs are basically the state of this array that you're having to solve. And then the output is basically the order and the piece that you're looking for. And the algorithm is the bridge that connecting these two things together. And what about methodologies? What are some of the stages of perhaps using computational approach to solving problems? And as you probably know, working or studying in scientific communities, the scientific approach to any questions is often to come up with a plausible hypothesis. And then you collect data, you plan out an experiment to test out your hypothesis. And the computational approach, however, focuses more on analyzing the size, the complexity, and maybe the sheer number of unknowns and knowns of a problems. And there are often 4 stages that are involved in solving a problems in this kind of manner. And the first is always to understand the problem. It might sound obvious, but a lot of times when we encounter problems, I think often just come straight into solving these problems without actually a proper understanding of the problem itself. And for example, a problem could be, I don't know, it's usually a problem. It's not just simply a problem, it's a layers of problems, and there's different problems on top of the problems that you have to solve, and not just that one big monolith problem in itself. And for example, a problem could be maybe given a number of numbers, a collection of numbers. You are asked to develop an algorithms to find maybe all the prime numbers in that set of numbers. And the first reaction that you should not be going for is to going into coding right away. And the first reaction is to first take a step back and maybe look at these problems and ask questions to clarify it. You should clarify, for example, what is the sample space that I'm working on? How big is this collection of number? Maybe 1,000 numbers or an infinite amount of numbers. These answers to these different questions would actually help to frame your mindset, and also maybe perhaps limit the number of possibilities you have to work with. And maybe what numbers does this collection start with? Am I allowed to use maybe an existing libraries, or do I have to develop a very bespoke solution to this problem? And when you go to these different technical interviews in these companies, a lot of times the interviewers expect you to ask questions about the problems before actually solving them. And asking question is the sign that you're thinking deeply about the challenge and not just blindly coding and hoping to find the answer while you're just doing it. And so if the problem is complex, the approach is to simplify it, to reinterpret it, to restate the problem in your own words, so that you yourself can have maybe a tertiary and also a deep understanding of what's going on. And it also might be very helpful to draw out the problem in a diagram, or maybe give it basically a pictorial representation so that you can understand it in a simplified format. And once you have a sufficient understanding of the problem, then you you set a goal of what you want to actually achieve. Then you start to consider the different strategies on how to find the solutions and devise a plan of actions to get there. And we'll talk about the strategies in a minute. So we'll move on to stage 3 here, which is the design of the algorithm. When you have worked out a path towards a solution in stage 2, then you actually start the coding process. And by this point, you can either start coding for real in a real coding language like Python, R, C, or Golang, or use pseudocodes, which is actually preferred in most situations. Pseudocodes is basically not actual codes, but instructions that can easily be understood and can be translated into any coding languages, which is basically instructions that looks like code. But if anyone, for example, your mother or your girlfriend or your boyfriend, if they look at it and they're not a coder, they can still understand what's going on. And with that pseudocode, you can translate that into perhaps like any kind of languages that you're fluent with. And the goal of this stage is basically to develop a proper algorithm to reach the desired output. And finally, the last stage is to review the whole solution pipeline that you have, and to perhaps reevaluate whether or not this is the optimal solutions, both in terms of time for executions and the space that is needed and the resource that is needed to store the solution space. And perhaps can we do anything to improve these different aspects? Is there a better or more elegant solutions? And is there a clever path, a more clever path to finding out like the final outcome that you want to find? Most of the time, a lot of problems will have multiple solutions, and it is in your interest to work out what is perhaps the most optimal solutions, or maybe during your journeys to figure out like some of the solutions that might be able to help you to solve this, because it's basically over time, it helps you to frame your mindset to optimize and to find the best things. And not just settle with just good enough. And also one thing that we would also be concerned with in terms of reevaluating the solutions is there any edge cases that we're missing in our solutions here? And this whole process can be described in this pictorially with this very simple image here. You have an input, you feed it through an algorithm, and then it outcomes the desired output. And the algorithm is basically step-by-step instructions to help transform your inputs and approximate the solutions in the output space. And so what about strategies? The stage 2 that we were talking about, there are several common strategies that are often used in solving programming and coding problems. The first and probably the most common thing that all of us go for when we encounter a problem is a brute force method. It's basically trying out the simplest and most obvious path to the answer. And many times this is the correct path, and it will lead us to a solutions. But most likely it is not the optimal one in terms of time to execute and also the space and resources that is needed to execute it. And brute force solution is, basically it's often sacrificed either time and space for executions or both. And so we will actually see an example right after this of what we're talking about in terms of this sacrifice. And this second, and actually the main strategies, perhaps our coup de grace in strategies in problem solving is decompositions, and what people often call divide and conquer. It's basically breaking down this big and monolithic and complex problems into smaller and more manageable chunks. And then we can focus on handling each of these smaller problems individually. And in doing so, we will be able to solve the big guys. Basically, we will be able to solve the big problems by solving the smaller problems that we have broken down. And the third and fourth strategies are oftentimes complementary strategy to support the divide and conquer methods. And that's the divide and conquer is basically our main workhorse in most situations. So for example, in generalizations and pattern recognitions, it's basically we test out simpler version of the problem that is given to us, and to see if perhaps we can spot a pattern, and maybe we can use to generalize it to the bigger problems. So for example, the common issues or maybe a common problem that we often run into when we do data science and data analysis work with big data is that we have a lot of data that we have to process, sometimes even 1 million rows of data points, and it's very hard to work with. And so we take the approach for pattern recognitions and generalization is that we would take out a very small sample space, maybe 200,000 or perhaps even 20,000 data points. And then we try to model and find the patterns on that small subsets of data first. And only after we have analyzed and perhaps we have done some initial analysis on that small subset, and we find maybe some common patterns and some insights in that small subset that we can perhaps then generalize to the bigger and full data sets. So the idea is that we work with the smaller problems to basically to understand the problem more condensedly. And then after that, we can start to generalize to the bigger problem space. Abstractions, on the other hand, it's a way to express an idea in its very specific context, while at the same time suppressing details irrelevant in that context. So basically the essence of abstraction is basically preserving information that is relevant in a given context and forgetting everything else, forgetting all the information that is irrelevant in that context. And we do a lot of abstraction, for example, when we create classes in object-oriented programming. As you probably know, we abstract away the details and just focus on the particular characteristics of a class. And we code up these characteristics in a class attributes and methods. And we perhaps can go to a couple of examples just to showcase how these strategies can work in real life. So for example, take one of the simple problems, finding a name in a phone book. For a human, it's a very intuitive task, but if you want to program a computer to do a very similar task, to find a name in the phone book, you have to be very specific in your instructions. And so the brute force solutions that we often come across is basically a very exhaustive solutions, right? You basically open a phone book, you look at the first page, you cannot find the name, and you just look at the second page, you cannot find a name, and then you just keep going on until you actually find that on page, I don't know, 599. And so as you can see here, for the brute force solution, it takes 600 steps until you can actually reach the outcome that you want to find. And for the machine pseudocode, as you can see on the right here, so this is, for example, it looks similar to Python, but it's not actually Python. And the idea of pseudocode is basically just write down the process that you want to, the instructions that perhaps you want to give to the computer, and perhaps even give to people, so that it's easy for them to understand and it's easy for the computer to actually compute. And so as you can see here, you load the notebooks, and for all the pages in that notebook, you look for the name, and only if when the name is found, then you return it. And the better approach and the second approach that we have is the divide and conquer, which is basically you also need to have a better understanding of the data, and you need to have a better understanding of all the information available. And so the suggested solution is this version here, which is first we know that the phone book is sorted in alphabetical orders. And so you actually split the phone book directories into half. And if the name is not in the first half, you get rid of, if the name is in the first half, then you get rid of the second half. And if the name is in the second half, then you get rid of the first half. And now you're left with 500 pages. This is basically what a lot of us do, I think, what we actually do when we look at things in the book, right? You split the book into different sections, and then you find the things that you want to actually look for. And so as you can see here, with this algorithms for divide and conquer, you can actually solve this problem in 10 steps instead of 600 steps here, as the brute force algorithms. And so in order to implement this in machine language, for example, as you can see on the right of the presentations here, you have to load the book, and then you have to actually denominate the lower half of the book, which is the first page. You denominate the upper half of the book, which is the last page. And then and as long as when the lower half of the book is less than or equal to the upper half, then you can keep dividing the book into half until you actually find the name that you're looking for. So every time that you go through these steps, the task is split by half. And so you have basically less time to execute, and it's a much more elegant and much more efficient solutions thing for the problems that you have at hand. And this is another examples of how you can perhaps use problem-solving techniques, computational thinking to solve the problems. So this is a problem. Please think about this and see if perhaps how many trains are running at the moment in Berlin. So this is the problem that I make up. So you can Google all you want. Please feel free to Google and find the answers. But you can also, yeah, perhaps if you have an idea, you can just type it in the chat. And even if you have a random guess, you can also just put it in the chat if you want to. And yeah, so this is basically, yeah. So let me go to the chats and see if there's any questions. Jeff Nana has a question. Yes, the presentations will be available after the session is over. So we don't see anyone putting up perhaps maybe a guess on what the solutions might be. So I'll just go through the solutions together, perhaps with you. So as we talked earlier, right? One of the first thing that we have to do is to understand the problem. So the problem here is we want to try to find out how many trains is running at the moment in Berlin. And this is actually what a lot of company called basically brain teasers. It's problems that really doesn't have an exact solutions, problems that really doesn't have an exact answer. And they give you this type of questions to test what is your thinking, what is your perhaps your way of reasoning and your way of working through a particular problems. And so this is one suggestion on how you perhaps can try to solve these kind of problems. And the way that if I would go about solving this problem is perhaps, as we talked about earlier, right? Divide and conquer. So do you divide these problems into smaller chunks that you can answer? And one of the ways to divide it is basically to divide it. In Berlin, we have the S-Bahn and the U-Bahns, right? The trains that runs on the ground and the trains that runs underground. And we also have international and regional train as well. And so it might make sense to actually split these into different things that we can solve. And you can see here in the process that have broken down, we first have to think about how many trains there are, how many train lines, both S-Bahn and U-Bahn are there in Berlin. And we have to think about how long are the average tracks for each of these lines. On average, how many train stations are there for each of the lines? And is this rush hour or not? And what is the average time between each trains? What is the average speed of the trains, S-Bahn and U-Bahn individually? On average, how long does one train finish? How long does it take for one train to finish one average line? And then, only then, when we find out how many trains are actually running on one track. And then with one track, we can actually scale the problem to all the tracks in Berlin. And so if you are able to maybe think about all of these different questions, then you can give the answer to each of these questions. And you do not have to have the exact numbers, right? Nobody, I think, in any interviews expect you to know exactly how many train lines are there in Berlin or how long each train lines are, but they expect you to be able to give a very reasonable answers on your logical process of thinking on how do you arrive at the solutions. And so with these, you can basically assume, for example, how many lines are there in S-Bahn. You can just maybe assume there's 20 lines of S-Bahn. There's 15 lines of U-Bahn, for example. And then you just gradually walk through each of these questions to finally arrive at the solutions and an answer. It might not be close to the answers of the actual answers, but because you have gone through this whole process, then they know that you actually know the process and you know the logical thinking to arrive at the solutions, no matter how complex a problem is. And so this is my answer for these questions. There's basically no real answer to the questions because I don't think there's any statistics except for perhaps Deutschbahn, who knows the exact number of trains running on that track right now. But this is my the answers when I look for online, for example, how long is the tracks in S-Bahn, how long is the tracks in U-Bahn, and these are the numbers that I actually found online. And when you plug all these numbers in, there's basically a total of 234 trains running concurrently in Berlin at the moment. And I actually gave this problems about 3 years ago, I think also to a group of Hertie students, and we worked through the problems together. And a funny thing is, everyone back then, they answered a different answer, but I think we have about 40 plus people in that room that day. But when you combine everyone's number together, and then you average them, it actually, we arrived at 231. So actually very close to the number here. And so it's actually also, it's a very interesting phenomenon, which is called wisdoms of crowds, which is the idea as that if you have, I think, the critical mass of number of people, then the combined knowledge and the combined information that everyone has is actually very close to the truth that you can actually have. And it's a very interesting phenomenon that is very well explored in super forecasting communities, in case you want to take a look closer into it. And so perhaps we can look at coding problems that is asked in interviews, for example, to see how this might work in a real coding settings. And let me share my screen for. Yes, for the browser. So one website that is very often used by computer scientists and also students in computer science and data scientists is LeadCode. It's a website that helps you to practice coding problems. And it's a very useful website. And you can basically code on the website and you can solve problems. And we can perhaps come to the very first problems that they have here to perhaps try it out a sample questions that they have. And it's basically a very good space where you can practice and you can learn more about computer science and computational thinking and problem solving. You can basically use different programming languages to solve problems. And you will be able to do live coding on here. And then you will be able to run and evaluate your code and to see whether or not your code and how your code is compared to other people's solutions. And so, yeah, this is, for example, an easy problems that they have on the website. Given an array of integers called nums and an integer target, return the indices of the two numbers such as they add up to target. And you may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. And so when you come to a problem like this, I think the first thing that is very helpful is to basically, as we talked about earlier, right, to actually restate the problems in our own words and to perhaps maybe come up with a couple of simple problems, a couple of simple samples so that we can understand the problems more deeply. So they are very kind on LeadCode to actually give us some sample examples here that we can actually use. So we do not have to come up with that, but if you want to, we can perhaps come up with some of our own, for example. So for an array of integers for num, so perhaps it could be an array of random numbers like this, and an integer like targets. So perhaps it could be something like 10. And the questions that they're asking is that they're asking us to find the indices of perhaps two numbers in this list, where the sum of them basically equals the target, which is 10 here. And so immediately, if we can look and we can see right away that 2 and 8 is one of those two numbers that we that satisfy the conditions of the questions, right? And so perhaps we can say the solutions here, as we can see, is the indices of 2 is basically 0. And the indices for 8 is 0, 1, 2, 3. So the idea is that we have to code up an algorithm that can give us basically these solutions, which is 0 and 3, which is the indices of 2 and 8. When both of them combine together, that give us 10. So I think we can break down these problems into very simple two-step solutions, right? First, we choose a number, any number, right, in the array given to us. Perhaps we can call it chosen. And second, we can perhaps find another number in the array where that missing number is equal to, and that missing number and the chosen number, when they combine together, they equals the target number. So this is basically what we want to do in our algorithms, and so what we talked about earlier, the brute force solutions of this problem is basically you look at all the numbers here, right? You choose a particular number, and then you look through every single subsequent number, and to find if there's any numbers when they combine together, they give us the target number, right? So basically, for example, we choose the number 2 here. And the next process is basically we choose every single number after 2, and we combine them with 2. And if that number plus the missing number equals to the target number of 10, then we return the indices of these two numbers. And so that's the brute force solutions, which is you have to go through one number and then you have to go through every subsequent number. And if the first number and the combination with all the other numbers doesn't come to the target, then you move on to the second number, which is 4, right? So it might make more sense to actually use this to demonstrate this more easily. So 3, 2, 4, and 6. So for example, the first number you choose is 3. And then you have to basically loop through this entire list. 3 plus 2 is 5. It's not equal to 6. 3 plus 4 is 7. It's not equal to 6. So you move on to the second number. 2 plus 4 is 6. So you actually find out the numbers that you're looking for is 2 and 4. And so that's basically the exhaustive and the brute force solutions. And so, for example, we can do it like this. So we basically choose a number. We have to iterate to the entire list for I in range length of the numbers. This is basically you choose through every indices of the number, right? And the chosen number is num. Right, and so this is basically, for example, so for the very first case here, it's number 3. If I is 0, right? And this second loop is basically to loop through all the numbers again. So the first for loop is basically to choose the number that you want to be in the first list, right? And then the second for loop is basically to loop through all the numbers in order to find the numbers that might, together with the chosen number, make up the target. And so that's why it's I plus 1 here, because you cannot take the first number again, right? You have to take the number after the first number. So that's why it's I plus 1, because it's basically one number after the first number and one number after the number that is chosen. And if nums j, which is the number that is the missing number, but it makes more sense to just say here missing equals nums. If chosen plus missing equals to target, then we returned indices. So let's go through this again to make sure that everyone's on the same page. So first, we have the first loop, which is the loop that we use to choose the numbers that we want to start the check with, right? And then we start the second loop, which is basically the loop that loops through all the rest of the numbers in order to find perhaps a number that is missing, that together with the chosen number give us the target. And we can perhaps run the code here and see if it works. Yeah, let's submit and see if yeah, so the solution here was accepted, right? And that's basically the first solution that we have, which is the brute force solutions. But is this the most optimal solutions? I would say that it is not, mainly because we have two for loop here. And when we have two for loop, it basically means that we are using a lot of time complexities in our solutions, because we basically have to double the loops and we have to double the time that we go through the entire array. And so our time complexities would be, if you go for complexity, it would be O of n squared, especially for, so for example, if we have 1,000 numbers in our array, then the number of times, and the worst case scenario is that the two numbers that we're looking for is the last two number of this entire array, right? And so we would have to loop through this entire array 1,000 times 1,000 times in order to find that two last numbers at the end of that very array. And so it's a very time consuming solutions. And so let's just put this here as a brute force. And then now we're looking for perhaps a better solutions. So let's look again at what we have to do. First, we have to choose the number. Right? Then we find the missing number of the array. And missing, that's chosen, is equal to target. So perhaps one thing that you notice is that when you frame a problem like this, maybe it's actually better to look for the missing number that you already know, right? So when we do a problem in brute force manners, we basically just look for every numbers. We do not have a specific number in mind. So we look for every numbers and we use that numbers to sum together with the chosen numbers in order to get the target. But we do not actually look for a specific number. But if we already have a target in mind and we have already a chosen number in mind, then perhaps we can actually find a missing number that we already know. And so that really help us to reduce the number of times that we have to loop through the entire array. And we can actually perhaps find a better, maybe a shorter solutions to this problem. And maybe we can have so And so one way is we can think about perhaps creating a list of numbers that we have seen before, right? Because we need to check in order not in order for us to know whether or not a number is already appearing on the list before, so that we do not have to loop the list twice over, and it increases the complexities of the problems. And first, we need to create that dictionaries where we can actually store the values that we have seen before together with the indices that it already has. And so let's choose the number in this sense first. It's very similar to what we've done before. First, we have to choose a number, and the chosen numbers here is as before, nums and I. And then this is where the steps diverge a little bit, because we talked about a complement, right? It's basically we take the target and then we subtract the chosen number from the target so that you find the complement. And then the idea is that you're not finding and you're not searching blindly for the numbers in the list. And now you actually have a complement, you have a numbers and you have a target in mind that you want to search for. And it simplified the problems on a much bigger scales. And so the idea is that now if we see the problem in the dictionary, then we return that list basically. And else, if the complement is not in the list of numbers that we've already seen, then we put the chosens in the list. Test it out and see if it works.
The in is missing for I in range.
Yeah, thank you. Submit and see if this is any better. Yes, so as we can see here, so the solution is accepted, and the runtime for the solution is, as you can see here, much faster than the brute force solutions that we have earlier. Yeah, and even though it's much faster, it's still only faster than 55% of other solutions. And so there are definitely much faster solutions out there. And so this is just basically one other solutions that you can see to help to optimize the problems that we face when we deal with coding problems. So we have seen basically two ways to solve the same problems, and each of them have their own benefits and of their own pros and cons. Right? The first solution, it's a very intuitive solutions. It's very easy to understand. You look at these problems and you can intuitively kind of think right away of the way to solve it. But it is very time intensive, because with a small number of elements in an array, then it can still be very fast. But if the size of the problem becomes very big, for example, 1,000 numbers, 1 million numbers, then these solutions would run into a lot of time execution issues. But with the second solution, as we've seen here, we are able to, with the very same process, actually, we are able to distill the problems into a simpler problems of not just finding any number, but actually finding a very specific number in the array, so that the numbers actually reduce and the complexities is reduced. And then, as you can see here, the time that is needed to run that executions and to find these solutions is also much quicker. And to come back to our slides. So as you can see here, today we have a couple of ways to solve coding problems and a couple of ways to think through perhaps computational problems. And where do we go from here? How do we keep perhaps training our mind to be familiar and to be able to solve more problems like this? And there are a couple of suggestions that I would like to put forward. So one is to keep practicing coding. So LeadCode is a very good platform for doing that. There's a couple of platforms that are very famous for, I think, coding interviews training. There's LeadCode, there's a Code War, and a couple others. They're all free, and you can find all of them all online, and you can code on their platforms, and you can run and execute, and you can compare your code with others on the platforms. And it's a very good way to upskills and a very good way to really, it's a good way to gamify, I think, the process of learning how to code and how to think computationally. But I think more importantly is to actually document every problems that you come into. So one way that really helped me when I was working through these LeadCode problems and coding interview is to actually keep maybe like a Jupyter notebook or maybe like some file documentations where you actually document every problems that you come into. And over time, you will be able to see different patterns of the same problems appearing over and over again. There is a searching problem, there's sorting problems, and there's all kinds of very similar problems that have very similar solutions to them. And so after a while, you will realize that you don't have to think of a new solutions every single time. There's actually a very selected class of solutions that you can go for almost every single time you come across these kind of coding interview questions. And so I would very much implore you to keep track of coding problems that you come across and maybe group them into these kind of patterns. And if there is interest in these patterns, we can perhaps also do a sessions on the patterns that I and also my colleagues have come across very often doing our line of work and perhaps doing our interviews with other institutions as well. Let me know in the chat in case you want a sessions just purely on these different patterns and on these specific coding questions and how to group them into these different types of questions on data structures and algorithms, on dynamic programmings, and perhaps on graph problems, for example. So yeah, that's my second advice, which is to actually group the problems into different categories that you can tackle all together. And then the third one is actually to try it out mock coding interviews. And there's a very good platform called Prompt, where you can actually schedule a peer-to-peer mock interview with other students who are also perhaps learning to code and also learning to apply to these different tech companies. And you can actually test each other after it. So because a lot of times when you do these screen tests, you're actually testing it together with an interviewer from the other side. And so they would give you questions, and then you can actually ask them questions, and they will give you maybe some hints or some answers to clarify on the problems. And so it really helps to actually go through this process of actually sitting down with an interviewer, do a mock interview, maybe with your friends, or perhaps on Prompt on the platform, so that you can actually get familiar with actually vocalize the problems and vocalize the process of solving your problems, much like I did earlier when I talked through how, like, what I was thinking about when I was thinking the problems, like how do I divide the problems into step one, step two. And it really helps to really frame your mind in a way that, like, how to actually vocalize the problems and how to ask for questions and how to find more details and how to actually explore all the space of the problem. And I highly recommend if you want to go for purely technical roles in a lot of these tech companies, then go through these three things: coding practice, categorizing your the coding problems that you come across, and then do the mock interviews to improve. And it really helps. It's very much like an SAT or a TOEFL test. The more practice you do, the more confident you are with these questions, and the easier it gets to solving these problems. And we also have a couple of recommended readings that you can also use if you want to perhaps train more your mindsets on how to do it. First is the art and craft of problem solving, a very fun book, a lot of fun problems. You can actually find a lot of brain teasers problems in here that some companies still use nowadays. Brain teasers are not used as often anymore because I think it's a little bit tough on the candidates to actually come up with a solution on the spot, but it still happens. So actually one of the interviews that I went to a very long time ago, I think 5 years ago in Korea, with a company, and it was a position for a quantitative analyst and finance positions, and the interviewers actually brought out like champagne bottles from his wine cabinet in the office and asked me, how many bubbles do you think are in this champagne bottles, for example? So these questions do come up sometimes in interviews, and it really helps to prepare it, and also to know like how to think through a problem like this when you come across them, and how to break them down into smaller chunks and to answer like the smaller questions before you answer the big questions. And then there's the book Computational Thinking, A Beginner's Guide to Problem Solving and Programming, a very helpful guide and it's a very same thing that I just listed out earlier, all the steps and all the stages, but in more details, and then give more examples on perhaps Python and how you can use the same kind of structures and the same kind of stages in thinking to solve Pythonic problems, for example, and algorithms to live by. A very fun book it's basically about how we can actually organize our life algorithmically to optimize all the decisions that we make. And it's a funny book in the sense that it's not something that you want to follow word by word, because it's basically like teaches you, I don't know, like how to find the optimum partners, like how to find the optimum, I know, wife and husbands, and how to make an optimal purchase in real estate, for example. I mean, I don't know if we want to surround our life only by computational thinking and not just with simple emotions. But it's a very fun book to read, I think, and to perhaps think more logically about our choices in life and how we can actually make use of computational thinkings in making better decisions in our daily life. And yeah, so that's come to the end of my presentations on computational thinking. Please let me know in the comments, and also if you want to reach out and let me know if there's any other topics that you are interested in that you might want us to do a workshop or presentations on. And yeah, I'll maybe take a few minutes for questions, and then perhaps we'll close off the workshop. Yes, thank you, Mukund. Yes, Sindru. Sindru have a questions on abstractions and modeling methods. And so abstraction and modeling. So if Sindru, if you work on object-oriented programming, abstraction is basically how you write a class in Python. And yeah, basically, whenever you write a class, you have to think about all the different characteristics of a class, right? For example, if you write a class about cars, you have to think about characteristic. What is the distinct thing about that cars? There's colors, right? And then methods, like what are the things that the cars can do? It can drive, right? And so it can also crashes, for example. And so abstraction is basically you take away all the details, like the colors, like you don't have to think about it, red, white, blue. No, you just abstract. What is it? It's a color. And you put colors as the abstraction of like all the other details. And it's basically one of the characteristics that makes up an attribute of that car class. And then what about all the other things that cars can do? Cars can, cars has all these engines and things that running with it, but all of it comes together. You can abstract it and say that it's just driving, right? And it's going somewhere. So you abstract all of these other components and all these combustions and engines and all that into this one thing that is driving. And then that's basically the idea of abstraction. It basically helps you, to simplify your problems into all of, and distill your problems into the things that matters in a particular context, and then leaving out all the details for a later thing, or maybe a later example. So that's the whole idea behind it. Yes, thank you everyone for your appreciations, and I also very appreciate your patience as well. Yeah, hopefully we can organize similar workshops in the future. Let us know if there's any topics that you would like for us to touch on in the near future. And with that, thank you, and have an absolutely wonderful afternoon, night, and day wherever you are, and take care. Bye bye.